Welcome to the webinar. The title of this webinar is YOLO V3, V4, V5, oh my. And I love it. And Joseph came up with this excellent title. And it's very exciting because, there is this family of object detectors that we will talk about, and also the controversy around all these versions. So this is going to be a very exciting webinar today. And let me ask Joseph Nelson, who is the CEO of Roboflow, to introduce himself.
Joseph Nelson, co-founder, CEO at Roboflow. At Roboflow, we're on a mission to enable any developer to use computer vision, and specifically make it even easier to train custom models, prepare data sets, deploy to any device, NVIDIA Jetson, web-hosted models, you name it. So we're an end-to-end platform that makes that process easier. A little over 30,000 developers have built with Roboflow for all kinds of use cases: manufacturing, retail, aerial image analysis. What's been kind of fun is, frankly, the limits of what people work on is just the limit of human creativity. As a part of that, we've come across quite a few novel model architectures that our users build with, that we play with ourselves internally, and kind of inspired a lot about what today's discussion is going to be on the YOLO family of models. And so today, Satya and I will mostly have a conversation and talk through some of the YOLO family of models, but some expectations, some things that you might walk away with. You might not know, for example, that there's a whole other model framework that Baidu created that creates and improves upon YOLOv3, YOLOv4, YOLOv5. We'll talk about that. We'll talk about the origins of the YOLO family of models. We'll talk about the evolution from one model to the next and the incremental improvements that we've seen. We'll talk about adapting them for real-world performance. And we'll also talk about how you can train a custom YOLO detector to your own data set towards the tail end. And as Satya mentioned, there's not, the YOLO family of models is not without a little bit of controversy, so we can touch on that as well. Some of the discussions that have happened in the vision community surrounding each of these models and their capabilities. So that's what I'm gearing up for today. Satya always leads a great discussion, and Phil is our steadfast moderator. So looking forward to the conversation today.
Yeah, so we will also be using Zoom's Q&A functionality today. Please submit your questions at any time during the webinar, and then we'll answer as many as we can at the end. And we'll also be doing a giveaway. Stick around for that towards the end of the show. I think you're going to like it. It'll be it involves raccoons, I'll tell you that much.
And as people know, people who are regular on this webinar know that Phil is the content manager at OpenCV, and he basically puts together the webinar. And I'm Satya Malik, I'm the CEO of OpenCV. I also forget to mention that all the time. All right, so let's get started. I think let's start with Joseph. Would you like to share the screen, and we will go over the evolution of YOLO first, and then we'll go over each new one, right?
Sure. How are we looking?
Oh, great.
So before we dive into just the YOLO family of models, I want to zoom in on which part of the computer vision process we're talking about today. So as you know, when you build and train a vision model, there's a lot of steps involved, everything from collecting your data, organizing your data set, annotating your images, pre-processing and preparing your data, training your model, deploying that model, and then displaying results and closing that active learning loop so you can do that on an ongoing basis. We're zooming in today on that train bubble, right? We're going to talk deep about architectural considerations and about the YOLO family of models specifically, which have drawn a lot of attention, and for good reason. They're incredibly robust. They also democratize the capability for training to be substantially less than that of other similar models, while not sacrificing performance too much or any at all. And so today's discussion is really going to zoom in on talking through the important architectural considerations. Now, despite that, and I know I've said this before on the OpenCV webinar when you all made the mistake of having me once previously, the architecture is not nearly as important most times as your data set. And having a high quality, representative, data set is always going to be a good investment to make, and probably going to be more important than, say, upgrading to the most recent detector. That's not universally true, but it's tended to be true in most cases. So
in
without
fact, I'd
further,
like to add to that, Joseph, that recently Dr. Andrew Ng, I think he tweeted or somewhere I read that he's thinking about a competition. Usually what happens is that you have a data set for a competition, and then you have different architectures. What he's suggesting, and this is very insightful, is that keep the architecture constant. Pick a popular one, right? Keep the architecture constant, and now your work with the data, right? You would say that collect the data, which will produce the best results on some unseen data. And I think that is so insightful, because that's how a lot of things happen in the real world. It's very rare, extremely rare, that you would go and look at a new architecture when you are engineering something, right? When you're in the research domain, it's different. But usually you pick a model that, usually based on the preference of the engineer, you pick a model and then you collect your data so that it gives the best performance, right? Usually don't make too many changes with the architecture. Even if you make changes with the architecture, it is usually that you pick a different standard model, right? A standard architecture, instead of completely changing things.
Yep. Yeah, I didn't know he was starting that competition. That makes a lot of sense. And I think it's emblematic of where rubber meets the road in terms of vision getting to production. A lot of the time, research considerations are unique from those of production considerations. And by that, I mean, in research, there's the ability to hold more things constant, especially around the data set, whereas production, and so in research, the data set might be constant, but the architecture is changing. Whereas in production considerations and conditions, almost the opposite is true, which is why I think Satya and Ring is thinking about flipping the script in terms of saying, actually, let's hold the architecture constant and think about the data set that we can use for improvement. Because if you think about it, when you're out in the wild, or you have a model that's, let's say, we have a user that they're attaching a model to, or attaching a oak device to a drone, and then they're flying that drone over top of a golf course to find places that require more maintenance based on the types of grasses they're identified. So there's Dallas grass and crabgrass and things like this. And you don't want those on the golf course. And what's interesting there is the grass can look different. There can be larger or smaller patches. The time of day could vary, how close or far the drone is flying from the ground, the approach the drone has relative to the course below. These are all considerations that are dependent upon the environment changing the data set, rather than changing just the architecture. And so I think that that's a insightful thing to think through in terms of model improvement, is really data set improvement.
Yeah.
Now, with all of that, I guess, caveat aside of the importance of the data set, we can talk more about the differences in architectures and where the YOLO family of models comes from, where it's at today, and where it's headed. So with that in mind, all about YOLO, it's a great name from the one and only Joseph Redman. Kind of maybe a fun quiz here would be, who could be the first to post Joseph Redman's resume in the chat? I promise you will not be disappointed if you pull up his resume. And actually, you know what? I'll pull it up towards the end of the webinar because I think it is a great testament to just being yourself and putting yourself out there. But it does give you some insinuation as to the thinking around YOLO, which, of course, in a lot of slang is you only live once, but in the context of computer vision, it actually stands for you only look once. So it's kind of a clever name for this architecture. And what's novel about YOLO is that it's a single shot detector. Now, it's not the only single shot detector. Things like MobileNet and MobileNet SSD in the context of object detection also are single shot detectors compared to two shot detectors. But what's unique about YOLO is the way in which it approaches the detection problem. So going one level up for a moment, when we talk about computer vision, there's a wide array of different problem types we could be talking about. We could be talking about a classification task, right? Which is like, is this, image not safe for work or not if you are doing content moderation? Or is there a dog or a cat in this image if perhaps you run like a site for adoption and people are uploading their images? But classification is basically adding tags to images, right? The ability to tag an image based on entire image contents. If you move one step to the right in terms of like depth of that problem, there's object detection problems, which are answering questions like, is this object present in the image or video? And where is the object present in the image or video? And with knowing the location of an object, that unlocks a whole new host of capabilities. We can do things like track an object to know its speed. We can know like when it's present or when it's not present. We can know precisely where it is. And each of those sorts of considerations in the field of object detection allow us to do things like build robots that can navigate the environment towards an object of interest, build quality assurance systems that say, hey, I see a defective good and it's at this spot on the supply chain. Build in the context of the drone over top of the golf course, say exactly where it's seeing problematic Dallas or crabgrass from its perspective above. And so that's in the object detection task. Object detection, by definition, is always finding bounding boxes. So we always label our objects with those rectangular or square shaped boxes. And then, I mean, just to round this out discussion, there's other types of problems, right? Like key point detection, pose estimation falls into that family, semantic segmentation, where we find the pixel map outlines of a given object. Now, YOLO fits squarely in the middle of these problems. It is an object detection model and family of models, first introduced, as we mentioned, in 2016 at CVPR, a research conference on computer vision. And it even won the People's Choice Award at the conference. It was a pretty marked introduction in its improvement. Now, to talk a little bit about the single shot versus double shot, or two-pass approach. So if you think about a model that is trying to find objects in an image, if you think about this problem and ignore any sort of architecture, ignore any sort of preconceived notions about the way you might tackle this, what we could do is we could say, okay, the first thing I want to do with this image is find the things that look like they're interesting objects in the image. And then when I find those things, I'll classify them, right? So first, basically draw bounding boxes, then zoom in on just that bounding box and make a classification for that bounding box, right? And this is what a two-stage detector is. A prominent two-stage detector, faster RCNN, which despite its name is actually traditionally slower when run on the same architecture as the YOLO family of models, is an approach that takes this two-shot detection approach, meaning, and if you think about it, it makes sense why that might be slower than a single shot detector, because we first have to pass the image through and find the areas of interest. Then we use computation to say what that box of interest, what class that box of interest ascribes to, which can be more accurate, but also can be more limiting in terms of the time and the types of devices we might be able to run that model on, the real-time performance, or even potentially the accuracy based on the problem type. Now, the YOLO family of models is in the single shot detection, which means at the same time the image is passing through the network, it is both doing the detection and classification task. And specifically, the YOLO family of models does this by dividing up the image into sub-regions. And those sub-regions are also tunable parameters. If you've ever trained a YOLO model, you might see something called like the anchor boxes. Basically, when you train a YOLO model, you might tell it where in the image to regularly look for regions of interest to be able to do these detections and classifications of the object in a single forward pass through the network. And you can kind of see, right, from doing a single pass, that might yield greater speed, and it does, in fact, yield greater speed, but it might also sacrifice some amount of accuracy. Now, what's impressive about YOLO specifically is its simple and straightforward approach to single shot detector resolved a lot of these concerns and inhibitions with creating high quality performance production worthy models with a single shot detector. And so the first YOLO model was a very notable breakthrough, and there were subsequent versions that we'll talk through here momentarily. So
So one other thing I would like to add just to what Joseph, you mentioned in two-shot detectors, what happens is that they are obviously finding all the possible bounding boxes, and they are then classifying it. In single-shot detectors, they are not looking for all possible bounding boxes. They have a collection. They are looking for specific kinds of bounding boxes, and they are saying that these bounding boxes can appear in these locations in the image. So the image is divided into grids. So obviously, when you're looking for a fewer number of bounding boxes and specific ones, and so once you find that bounding box, let's say a cat, it's usually not accurate enough. Then you do some regression. You actually manipulate that bounding box so as to fit the cat better. So that's even after doing that regression, that's why, because we are looking for a specific number of bounding boxes, it is fast, but it's also less accurate than two-stage detectors. But in many real-world applications, that's what you need. You need speed and accuracy. As long as it's inside that box, the accuracy is not, it's important, but as long as it is in the box, we are okay. The one other thing I would like to say about YOLO, when it was first released, the first version of YOLO, it would work very well, but it also had these limitations that the way it was constructed, it also meant that you could not have, let's say, I cannot remember the exact number, but let's say 10 objects in a row, right? Just because of the construction of the architecture, it assumed that you would not have more than 10 objects in a row. If you had more objects, then it would simply detect 10. But those are engineering optimizations, right? You have to make those choices because in most cases, you're looking at pedestrians or cars, and there are a few of those, right? But with subsequent versions of YOLO, that it's not that restricted. It's not 10. It's a much higher number. And the second thing, somebody was asking me a while back, a couple of years back, is YOLO the best detector? And I said that YOLO may not be the best detector. I don't know 100%. It depends on your application. But YOLO is definitely the most colorful one. It is the Lady Gaga of object detectors. Look at the website. Look at the .NET website. Look at Joseph Redmond's resume. Look at all the controversy that has happened. So it's I like to call it the Lady Gaga of object detectors. You cannot ignore it.
I like that. I like that summary. And what's kind of funny is that like these models almost like the architecture is almost like developed fandom like sports teams, which was always so funny to me. It's like, like I'm like Team YOLO, or like I'm like faster RCNN, or like I'm efficient det. And I guess that's plays into something in human psychology, I suppose. But in general, it's really just, we take the approach that whatever model is going to be best for the job is probably the one you should use. And YOLO's contributions are these speed and single pass detectors. And one thing that, Satya, I really appreciate you calling out the engineering optimization to cap the number of classes that are happening in the detection. Another limitation that is still present even in future YOLO versions is, in fact, the YOLO family models may be more likely to struggle with small objects, especially if they're at a great distance from the frame. And part of that's because in the pursuit of optimizing of where the anchor boxes should be and training the model to identify specific regions of interest in the image, it just has and treating it like a regression problem, it may have a tendency to, all things equal, miss the small object compared to other architectures like faster RCNN, which if you think about the broad strokes we're talking about of the comprehensive kind of deep search across all the image and then classify, it makes sense that might be a bit more comprehensive as an approach. Now, how small of an object is kind of like the follow-on question, like how big or small does the object need to be? And that's, again, one where you have to answer empirically. Anecdotally, I think that there's potential for drop-off if you have very, very, just 1% to 2% of pixels of the overall image type problems can be an issue. And of course, there's other optimizations you can make with small objects that you can make with the YOLO family models, or you can make with any family of models, like increasing resolution size or tiling your image as a pre-processing step and things like this. So that doesn't mean it's necessarily immediately inhibitive of being able to use this architecture. But I do want to note that all things equal, this detector may struggle more with that type of detection than others. I saw a question in the chat that's actually relevant at this point as well around the framework and architecture that YOLO was implemented in. So Joseph Redman, when he introduced the YOLO framework, he was also introducing a framework called Darknet. And he still actually works on Darknet to some degree. I mean, Alexei AB, as he's known on, Alexei Borchovsky, who made YOLOv4, is kind of the main maintainer of Darknet now. But Darknet is a framework much like that, like PyTorch or TensorFlow, for implementing neural network primitives. Now, Darknet, because it was built, kind of for this specific architecture, and these, well, I shouldn't say that, but it was built by one researcher as opposed to like having the institutional backing of like Google with TensorFlow or Facebook with PyTorch. It does not have the same sorts of optimizations and ease of use and usability, and it's native to C. And so that the developer experience of using Darknet and in making improvements and changes has been more challenging than that of others, right? Because a lot of those that are working with models are pretty familiar with, say, Python more than they are C or C++ for making optimizations and changes. And so that is a notable thing, is that YOLO v1, v2, and v3 were all native to the Darknet framework. Now, because of the popularity of these models, some people have taken the architectures and re-implemented them in other frameworks, and we'll talk more about that. But it is one of the things that I think limited the ease of use and certainly production-grade adoption is Darknet not being as familiar to developers that are working on these models as other similar frameworks.
Cool.
So I think maybe what we could do is so with YOLO being introduced, Satya hit on some of the key limitations. It was still, a breakthrough in terms of a single shot detector that could be so successful, but it did have these limitations in terms of class limits and things like that. Joseph Redman and his research colleague released the YOLOv2 paper. It's actually not called YOLOv2 as the paper, it's called YOLO 9000, because it was, again, kind of a joke of like, oh, it's over 9,000, right? If you're familiar with this sort of meme. So to Satya's point, the Lady Gaga shines through brightly. And that made some optimizations and improvements around some of those limitations on class size and things like this. And then YOLOv3 was released. And that's where things really, the dam kind of broke, so to speak, in terms of like awareness and adoption of the YOLO family of models writ large. And so YOLOv3, the YOLOv3 paper, which I have here on the right side, the first page, released in 2018. I have the abstract on the left, and this gives you a sense of the difference of research style and approach than that of others. We present some updates to YOLO! Exclamation point. I mean, first, right off the bat, when's the last time you read an exclamation point in an archive paper? We made a bunch of little design changes to make it better. We also trained this new network. That's pretty swell. It's a little bigger than last time, but more accurate. It's still fast, though, don't worry. At 320 by 320, YOLOv3 runs in 22 milliseconds. That's 28.2 map, as accurate as a single shot as SSD, but 3 times faster. When we look at the old 0.5 IOU map detection metric, YOLOv3 is quite good. It achieves 57.9 AP50, mean average precision at 50%, in 51 milliseconds on a Titan X, compared to 57.5 AP50 at 198 milliseconds by RetinaNet. Similar performance, but 3.8 times faster. And so the colloquial nature and adoption, I mean, YOLOv3 paper is particularly, I'll call it approachable compared to the YOLO and YOLO 9000 paper, but it is a fun read, and it gives you an insight into some of the improvements. And if you're new to like kind of the object detection architectures, it is actually kind of a fun place to start for this reason.
Yeah, and look at how, if you look at the title, look how he downplays the paper. It says YOLOv3, an incremental improvement. That totally downplays the contribution of the paper. And I think the style really shines because he knew by this time that, the YOLO family is being adopted, and he could be completely on his own. People want to read this, right? What he has to say. And I think with this style, we also get a lot of confidence in somebody who's, who's so open about all the the metrics that they are reporting, they have done their best to make it, it's accurate, etc. So I think a lot of people are drawn to that aspect of, Joseph Redman also.
I did highlight one of the lines in the paper here in the introduction. Sometimes you just kind of phone it in for a year, I didn't do a whole lot of research this last year, which I think is just the level of intellectual honesty and candor and directness and simplicity is an appealing part. Basically, Joseph Redman's personality shines through in his work, that he doesn't take himself too seriously, but yet is moving the field forward in pretty dramatic moves.
Also extremely relatable here in 2021.
So YOLOv3 came out in 2018, and it really, as you can see in the paper in the upper right-hand corner here, the improvements on the COCO data set compared to other prominent models at the time, RetinaNet 15, RetinaNet 101. And what you'll notice, right, is the emphasis of the YOLO family models on speed, right? So you see here that it is quote unquote off the chart on the left in terms of how quick it is in comparison for similar benchmarks, but it doesn't maximize mean average precision to the same degree as some of these larger and more expensive to train, more expensive to run architectures, which really does get to the point that, like, when someone says, what's the best architecture ever, this is why so often the answer is it depends. Depends on your goal. How much compute do you have? Where does the model need to run? And these sorts of considerations. And one of the reasons that the YOLO family model is so prominent is because by being such a small architecture, it reduces the barriers to entry in terms of the training hardware you need to have, even in terms of actually the data set size and the efficiencies that it makes with some of the augmentations, which we'll talk about in YOLOv4 and YOLOv5 momentarily. But it really is a play to democratize things. And that's one with which, by definition, can reach a wider array of people and increases the popularity of this framework. So I think the YOLOv3 was also one of the first architectures to be implemented again in other frameworks. So there's a prominent Keras implementation, there's a prominent PyTorch implementation, but then notably at the time, shortly after YOLOv3, Joseph Redman determined that he was concerned with some of the ways his vision research was being used, and stepped away from doing vision research as a field. And so there quote unquote would be no YOLOv4 or YOLOv5. But in fact, I guess we kind of spoiled the lead with the head of the title of this webinar. Those things do exist, and we can talk about who kind of carried the torch from there. So the YOLOv4 paper YOLOv4 model was the first model to be released by an author besides Joseph Redman in the YOLO family of models. And actually, YOLOv4 is quite similar to YOLOv3, and it built upon actually a lot of data augmentation and data preprocessing type steps to make its improvements just as much as it did things like improving niche activation functions and CSP-izing the network, if you will. And I will share more about that in a moment. But I do want to touch on the contributions of YOLOv4 in the form of the ambitions and the goals. Okay, so I was talking about how the YOLO family models was meant to be a place for dramatic improvement. So I pulled a quote here on the left-hand side from the paper. We hope that the designed object can be easily trained and used. For example, anyone who uses a conventional GPU to train and test can achieve real-time, high-quality, and convincing object detection results. And that kind of gets you to the ethos of this architectural family of being able to make things more approachable and easier. And you'll notice that with YOLOv4 being released in April 2020, you can see its comparison to other popular detectors at the time, with efficient DET holding the record on the mean average precision on the COCO data set. And you can see that the Pareto efficient YOLOv4 does quite well in terms of the frames per second it's able to achieve relative to the same levels of accuracy on the COCO data set, right? So it's, again, in the incremental improvements realm of things, but all focused on speed.
Yep.
One other thing I will note about YOLOv4 is it was, again, native to darknet. Alexei Borchovsky, the main author on the paper, kind of took up the darknet torch and continued, and does to this day, continues to maintain and improve the darknet framework. But similar to YOLOv3, YOLOv4 has also been implemented in other frameworks. Now, one other thing to note is that after YOLOv3, as we mentioned, Joseph Redmond stepped away from vision research. So there was a lot of others who stepped up and started to do other types of work. Glenn Jocker being one of those. So he's an individual who did a lot of particle research and physics work, and he was using object detection for measuring the changes in particle physics, which is far, far, far beyond an area where I have domain expertise. But in doing so, Glenn had made a number of improvements to the YOLO architecture as well, in terms of optimizations and performance changes. And one of the big things that Glenn introduced was actually taking the YOLO architecture and then porting it to PyTorch, where he found it was easier to manipulate, improve, experiment with layers, drive to production. And when you're connected to the PyTorch ecosystem, then maybe it's easier to do things like deployment and improvement and things like this. And so that culminated.
As far as I remember, he did that for YOLOv3, right? The PyTorch. Yeah. Okay.
Yes. Yeah, that's a great call out. So as we were discussing how YOLOv3 was natively released in darknet and others ported it over to other frameworks, Glenn was one of the individuals that ported YOLOv3 to PyTorch and maintained the prominent repo of YOLOv3 in PyTorch. But over time, he continued to make these improvements that, like, suddenly the model didn't look like YOLOv3 anymore. It had a lot of different changes of data augmentation steps and things like this. And so there became this point that that Glenn thought about of what would it be like to kind of release a lot of the changes that I've made, but for others to collaborate on. And so that, in fact, results in the culmination of YOLOv5. So less than 50 days after the release of YOLOv4, YOLOv5 improves on state-of-the-art for real-time, and it was the first in the full YOLO family models to be fully implemented in PyTorch. Now, you kind of have to put first around air quotes here, right? Because he was also the person that re-implemented YOLOv3 in PyTorch. But in terms of like introducing a new model, this is the key thing here. Now, he noted that many places that the name may change. I think it's actually probably here to stay now after the awareness of it. And that it's under active development. So this is where we get actually to the kind of the change of traditional research in production. So in research, you typically release a paper associated with the introduction of your model. And you describe the changes you've made, summarize those, and allow others to peer review, check, improve, and kind of read and present. YOLOv5 doesn't have a paper. It was just and is released as an open source GitHub repo. And it continues to be changed and adapted, which means that it's actually quite hard to pin down exactly what and where the current version is without having a bookmarked point in time in the form of a publication to say this is what's new and different. But some things that are new and different about YOLOv5 compared to YOLOv3, for example, is YOLOv5 includes a lot of data augmentation by default in some of the training. It introduced actually YOLOv4 introduced cutout and mosaic augmentations, but Glenn was actually the first person to implement those in a YOLO training pipeline, and the YOLOv4 team adapted those and used them in their release of YOLOv4. And so he used those same sorts of improvements, but put them natively into the YOLOv5 implementation. And so maybe I think one of the key things to realize when you're approaching the YOLO family models is to recognize that, in fact, while the numbers give the appearance of being sequential, we're kind of in a spot now where we're totally forking in different places, that different authors doing different things, and there's no sequential nature to it. It's almost like, I don't know, if Disney made a new Star Wars movie, and then OpenCV got into the movie business and made the Star Wars episode 18 or whatever, just jumped straight into the future, and there's a whole new plot and you use some of the same characters. Now, of course, in the context of things like that, intellectual property rights would not allow OpenCV, Satya and Phil, I'm sorry, you wouldn't be able to release Star Wars 18 right now. But that does kind of give you the idea of how non sequitur the connection is, despite the name being similar. And because it's, researchers are generally open, there's frankly, kind of no reason or no need to like copyright like the name and say, this is like YOLOv3, YOLOv4, and whatnot. It's more just a community of people that want to improve the state-of-the-art detectors and provide attention to their work in doing so. So long story short, the naming convention induces confusion, but the net is it is still a single shot detector. It does include a lot of the improvements for speed and ease of use. It's native to PyTorch, which makes it a little bit easier to work with and train. And it's maintained and actively developed without a published paper, but with an active community around it. So that's kind of a bit of an overview of where YOLOv5.
Do you have any scoop on what people are thinking about? Because you guys wrote a post on comparing YOLOv4 and V5, and you talked to them directly as well. Now, the question I had is, do you know what happens with YOLOv6? Are they going to take even and odd numbers, or what is it? What's going on there? Or the name?
Your guess is as good as mine as to what happens with if there even is a V6. What's funny is that, like, in theory, anyone could kind of just like the thing that the YOLO like V5, like it felt like taboo to suddenly just like claim that when like it's like not it's not Joseph Redman. So can you really like say that it's in the YOLO family models and this sort of thing? Anyone could kind of just release V6. That's sort of what we've seen. Like V1, 2, 3 was Joseph Redman, but he's even tweeted and said, I don't care to say, like, if people want to advance research, they should advance research. And so I think that we'll probably have a V6 just because someone will want to like jump on maybe the branding train of sorts. Who will do it and who will maintain it and improvements that it will make? Your guess is as good as mine.
Got it. So one way to think about YOLOv4 and V5 is that, just think about it as them separate but related models, right? The development would take just different paths, right? Some good ideas may be borrowed from one to the other, but there is no active collaboration between the two groups. Is that a fair way to say it?
Yeah, I think it's a fair thing to say.
Okay, so okay, but let's look at the details.
Yeah, so as you mentioned, like we were able to connect with Glenn directly and talk with him about some of this, and we've posted some thoughts and videos, and we've also written extensive posts describing and comparing and contrasting a lot of the benchmarks and whatnot. But I think like the headline thing to be aware of is that when Glenn released YOLOv5, he had motivations where he said the main goals are ease of use, exportability, low memory requirements, high speed, improved map, especially via augmentation, and market size, increasing the range of performance so that there can be a higher practical user base of people that derive value from this technology. Which, again, to the very, very early point of this conversation that we teed up, the goals of research and production are often a little bit different. Mm-hmm. And in research, it's hold the data set constant and try different architectural considerations. In production, you can kind of change both, or you might just be focused only on map. You might also have things around ease of use and the ability to connect to a broader ecosystem and community. And so I think what's sort of funny is that like that's what the what YOLOv5 has often kind of stood for a lot of people is it's not all about maximizing Cocoa performance. It's also about getting to production quickly.
Mm-hmm.
Okay. Now that's not without some level of questions and thoughts in the community about what this stuff kind of looks like. Before diving into some of those questions that have come up, I do want to also mention that even when YOLOv5 was released, there was even discussion if it was even better on the Cocoa dataset than V4. And so this is actually kind of an old snapshot of when it was released, old as in summer 2020. I think it's captured in July 2020 on the repo. And the YOLOv5 large, the largest version, does improve over YOLOv3, but at the time, it wasn't necessarily better than YOLOv4 on the Cocoa benchmark. But this begs the question of, is Cocoa the right representative benchmark for real world conditions? It's sort of the norm, but does that mean it's the best for your type of problem and this, that, and the other? It basically highlights that, it's not all about the race for map on Cocoa. It's about some of these other considerations that you might want to have improve and keep in mind.
Right. Right. So, I mean, it would be nice to just explain this, because this chart we have seen at this, resolution for the first time. So people who may not understand this fully, could you please explain, the average precision, and also basically explain this graph so that people who are new can learn.
Yeah, that's a great call out. So on the y-axis, you have the average precision on the validation set in the COCO data set. So when we are measuring models, we care a lot about, did they draw the box in the right spot, and consider that to be the correct object. And if they do that 100% of times, then it's 100 map. Every single object was correctly identified. The COCO data set is famously pretty challenging. Microsoft released it in 2014, and it continues to be a useful benchmark for these object detection tasks. So basically on the left-hand side, on the y-axis, you want to be as high as possible to prove that you're identifying the 80 classes in the COCO data set with accuracy and precision. On the x-axis is average latency. So it's a measure of speed in a given batch size, with batch size being the number of images that you're processing, which commonly multiples of 32 or multiples of 2, so in this case, batch size of 32. And in this context, to the right means that you're processing a higher throughput of images, or excuse me, to the left. Sorry, higher latency. We're measuring latency. So you have if you're further on the right, then you have an increased amount of latency, which means you're taking longer to process images. So if in the ideal sense, an ideal model would be in the upper left-hand quadrant, where you have extremely high validation accuracy, mean average precision, and extremely low latency. Now, that's actually a good call out, Satya, that sometimes the x-axis on these things can change. So sometimes they'll measure speed instead of latency, as we saw with the V4 paper. So here, the V4 paper, the x-axis is frames per second, which is not a measure of latency, but a measure of speed. So in this case, you want to be further to the right. In the context of latency, we're measuring, how slow it is. So we want to be less slow. Now, this presentation here is the most common presentation. Typically, we measure latency. Now, the other thing to note about these presented graphs is there's this idea of Pareto efficiency, which means that if you increase your accuracy, your speed may decrease. Or maybe a better way of putting it, if you're sacrificing accuracy, you hope you're gaining speed, right? So any of these dots, you would hope to see the shape that you see here, which is kind of like that, exponential decline function in terms of performance. And that means we have an efficiently trained model if we are seeing that behavior.
Cool. All right. So do we have any examples of training one of these models that we can go over quickly?
Yeah, I do want to give one quick shout out to another architecture, and it's often not considered. So there's another architecture called PP YOLO, and it stands for paddle paddle. So Baidu, the search engine, kind of like Google of China, if you will, Baidu has a implementation of YOLO in their framework called paddle paddle. So paddle paddle is similar to PyTorch or TensorFlow or Darknet. And the researchers implemented YOLO's architecture in paddle paddle, made some improvements. And there's actually been PP YOLO1 and now PP YOLOv2. And they note that they've made improvements as well, right? And so, again, this gets to the point of if you're just aiming to maximize frames per second and the mean average precision, then maybe you would grab PP YOLO and implement that and bring it to production. But maybe, again, paddle paddle might be a new framework to you. So that might be a bit of a whole different risk and consideration of the deployment pipeline overall. So yeah, in terms of training these things, so I have a couple of recommendations. So on models.roboflow.com, we have a host of object detection models that someone could take and train and adapt to your custom data set. And so you could grab the Colab notebooks for any of these, and Colab is sort of a free training that does have limitations, but at least allows you to poke around and give things a go. And so you can try out the YOLO family of models. So like this is YOLOv3 implemented in Keras. This is YOLOv3 implemented in PyTorch. You also have YOLOv4 and Darknet. One type of model we didn't talk about, sorry, was a YOLO Tiny models, which you'll see there's YOLOv4 Tiny, there's YOLOv3 Tiny as well. Basically, it's the same architecture, but with fewer layers so that the speed is faster, but the accuracy is lower. And so we have implementations of even Tiny, which can be really good for embedded devices which have limited compute. And then even YOLOv5 as well, if you wanted to give that a go and train it. And even more information about each of these models, right? If I wanted to know more about any of the performance or the graphs that we were talking about here. So those are all open source and easy to use and implement. We've also created videos and blogs about how to use and train these models as well. And this is something that we aim to, again, make easy for people to get experience with using and trying. So fully walk through soup to nuts, end to end, everything you need to get going with training one of these models.
That's great. So we have 15 minutes left. Do we have more things to cover, or can we go into the question and answer round?
I think one thing we might want to touch on was the controversy point around some of the names in some of this. So one thing I do want to mention with the controversy overall is this tweet here. People were like, oh, they're quibbling about, is it legitimate to name one thing one or name it another thing? And so finally someone said, you know what, Joseph Redmond, you're the authority. You're allowed to say, do you approve? Are we allowed to do this? And he says, it doesn't matter. It doesn't matter what I think. And he mentions at this point, Alexi AB, who's been the maintainer of Darknet, he says has the canonical version of Darknet in YOLO. He's put a ton of work into it and uses it, not mine, haha. And this was in response to naming the next model YOLOv4. And Joseph Redmond has made similar statements around the other naming and these sorts of things. So a lot of the times the naming controversy, I think, gets caught up in the wrong focus. I think it's kind of, again, the wrong thing to think about. It's almost like, if you ever hear the Python versus R debates, it's almost like it's really not a place to spend your time. It's maybe a fun place to waste a few hours on Reddit, but certainly that's not really moving the ball forward for a lot of folks. That's kind of how I feel about the naming sort of stuff here. Is it's a fun thing to kind of chide about, but at the end of the day, when you want to build and train your models, you should do what's best for your context. And it's good to see that others in the field, like Joseph Redmond, have expressed similar sentiment.
That's a great quote.
Yeah, so do we want to do, lately we've been doing trivia first. Joseph, would you like to tell them what they'll win?
Oh, would I ever? Yeah, so at Roboflow, we our unofficial, and I guess maybe one day he'll be promoted to official mascot is a raccoon. And there's a lot of reasons for that. Maybe the raccoon data set. Maybe that Roboflow raccoon sounds like a great alliteration. Maybe that Roboflow improves your trash data and raccoons love trash. I don't know. There's a lot of reasons to believe that the raccoon is prime for promotion. Well, we actually had an artist. We contracted an artist and said, "Hey, make a design of a raccoon for us, and we're going to put it on some T-shirts. And those that contribute novel things to the ecosystem. So those that write blogs on the Roboflow blog or make videos and show things about using Roboflow for training or annotation or deployment or things like that. We send these raccoon shirts to. And so that's what you are able to win today. In fact, you'd be one of the only ones to win one of these shirts that may not have already published, say a video about using the product or training your own model or things about any of this ecosystem. I can pull up a photo here in a second. I'll stop my screen share and pull up a photo so you have an exact idea of what the design is. But Phil, do you have the question in mind while I pull up the photo?
I sure do. So here's how it works. I'm going to ask a question based on the slides in the webinar here. And the first person to answer in the chat on my screen correctly will win the shirt that Joseph's going to show you a picture of here. According to the paper shown earlier in this webinar, in what year was YOLOv3 released? Whew, slow down, folks. Some of you were too quick on the draw. 2016, incorrect. The correct answer was 2018. It looks like Alberto Garcia was the first one here on my screen. Congratulations, Alberto.
So this is the Roboflow raccoon shirt.
Love that shirt.
Yeah, we had an artist, Von Dion, who does amazing work. He's colloquially known as Flower Boy, in collaboration with a group called Black Art House, which improves the promotion and work of Black artists. And so Von Dion made an amazing shirt for us. And yeah, can't wait.
Beautiful shirt. Beautiful. Definitely. So yeah, congratulations. Thanks, Joseph. I'll get you in touch with the winner and you can figure out shipping and stuff. Shall we go on to questions and answers?
Sure.
All right. Starting first with a performance question. Is the YOLO architecture less compute demanding compared to MobileNet on edge devices like, say, OAK-D or Jetson Nano?
Well, so they're two different things, right? This architecture is basically the architecture for, it's a software architecture, right? You can create a YOLO version, and if the format is right, you can run it on, say, OAK device or Jetson Nano, right? So you can take any of these models that we had shown and run with the right, when the format is right, you can run it on any of the Jetson Nano or OAK-D architecture. So they're two different things, right? One is a software architecture and the other is a hardware on which you can run pretty much anything.
Would you say one is sort of more performant than the other, I guess, is the question in terms of the single shot detectors? Is YOLO the king of the hill with regards to performance per, watt or whatever?
Right. I don't know about that. Joseph, do you know which one would be more performant on, said Jetson Nano?
So YOLO comes in various sizes, YOLOv5, S, M, LX. YOLOv5S is faster, all things equal, on, say, a Jetson Nano than a MobileNet SSD V2. And also more accurate, at least in the context of the COCO dataset or in most benchmarks that we've run. But of course, past performance is not perfectly indicative of future results and all those sorts of things. So in general, there's been, in most cases, in my experience, the Tiny YOLO is probably the exception here, but in my experience, YOLO almost always outpaces for a lot of the problems that I tackle compared to MobileNet SSD V2. The key advantage of MobileNet SSD V2 is that, it's native to, or not native to, but originally released by the Google team and in TensorFlow, and the TensorFlow ecosystem is really rich with the ways in which doing implementation and things. So in general, I think if you're doing stuff on the edge with limited compute and your detection task is not terribly challenging, Tiny YOLO or even a smaller YOLO model can be a good way to go.
That's great. Sorry, whoever asked this question, I completely misunderstood the question and answered the wrong thing. So I'm glad that Joseph answered it correctly.
Oh, good. We got there. Next question is about, are there any plans to integrate YOLO models directly into OpenCV distributions? I've got a couple of this question.
So OpenCV has a model zoo, anything that can be, so there are a lot of models that are supported on OpenCV, and YOLO is one of them. I cannot remember exactly whether YOLOv5 and V4 have made it yet, but we constantly keep adding models, right? The other thing is that anything that is implemented using OpenVINO, if OpenVINO has an implementation of that, then you can easily assume that OpenCV will run it, right? Because one of the backends that OpenCV uses is OpenVINO when available. And if it's there in OpenVINO, it will run in OpenCV as well.
Awesome. Thanks for that. I've got another question here about sort of about performance, but it's more about size. What What's the smallest object you've seen YOLO, any flavor of YOLO accurately detect? This is for either of you.
So accurately and consistent accurately are very different things. We have a user that I was talking to of Roboflow that's building a tool for identifying surfers from cameras that are far, far, far away on the beach. And the surfers are just minuscule in these images that the user shared with me. And he's been training all sorts of different architectures, and YOLO is performing sufficiently well on those very small objects. Now, of course, it's not perfect and not every small object is detected, but a lot of cases, like ultimately, like to make that question into one that I think might be actionable, my response in a way that might be actionable, the thing I would think about is, based on the problem you're solving, does the vision model need to be additive? Like, does it substitute otherwise like human effort, or does it need to be all or nothing? And if it can be additive, then it's just a question of finding the right threshold at which you can improve the process and probably increase the operational excellence. Think about, like, for example, if a human otherwise has to review and look for all these small objects, well, then the model, even if it's 30% of the time accurate, reducing human effort 30% is still a net gain, which is a different type of problem than saying, are we fully able to use this solution or not? Like, are we only going to use this model or not? And in those contexts, I think it's a bit tougher to figure out places where you can immediately transition, especially in small objects. And so it kind of gets back to a bit of what we talked about in the first webinar around the right way to frame a problem in a way that you can be successful with it.
Yeah, and piggybacking on that a little bit with regards to how to frame the problem, this one's almost philosophical. How would you recommend people decide when to use something like YOLO versus traditional computer vision for object detection and tracking and things like that?
I think for object detection and tracking, you just go for a deep learning model now, right? That traditional computer vision, there are a few cases where you can maybe get away with it. Simple tasks like, okay, for example, face detection, right? That is a very good, OpenCV has a very good implementation, but then deep learning models will be more accurate, right? One reason to use face detection in OpenCV would be, it's just out of the box, so you don't have to worry about it. It's just there, right? And if your application doesn't demand very extreme poses or extreme lighting, etc., you can just use it, right? It's hassle-free. But for most object detection tasks, I highly recommend that you're using for a serious project, you have to use a deep learning based model. I mean, it doesn't matter which one. You'll have to experiment which one you want to use. You can use YOLO. You have single shot multi-box SSD models. You also have EfficientNet and our current favorite. In our work, we have been using CenterNet a lot. That's another architecture. Maybe in a future webinar we can talk about it. But that's another one that people can try out. But effectively, we have noticed that it boils down to doing some experiments and figuring out which one works the best for your problem.
Anything to add to that, Joseph?
Yeah, I firmly agree. Empiricism and experimentation is probably going to be king. And then if there's any rule breakers that it needs to run in a small environment or things like that you can roll out some architectures.
Right on. You want to take us home, Satya? We're at the hour.
Yeah, well, that is it. And thank you so much, Joseph, for coming again on this and presenting this. I really love the title as well as the content of this webinar. Whenever you show up on our webinar, it's a blast. We have a very good time, and it's very educational for people. And thanks, Phil. That's, as always, for conducting and maintaining this webinar series.
Yeah, and as a reminder, this webinar will be uploaded to the YouTube channel, which I linked in the chat a little bit. We'll also post it on the OpenCV LinkedIn account, and we will be back here next Thursday, 9 a.m. as usual.
Thank you so much.
Thanks all.
Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. Today's episode was brought to you by OpenCV.ai, the world leaders in computer vision and artificial intelligence consulting, hardware, and software. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.